Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the structure and properties of phenol. We're going to talk about what phenol actually is, the structure and bonding in phenol, why phenol is able to act as a weak acid, why phenol reacts more readily than benzene, and look at its solubility in water. Quite a busy video. The reactions of phenol and the mechanisms are outlined in separate videos. Check the links in the description below. Before we talk in detail about phenol, there are a few essential ideas you need to be comfortable with. Benzene is a cyclic hydrocarbon with a delocalized electron ring. There is a pi bonding system where delocalized electrons exist in rings above and below the plane of the carbon ring. This gives benzene its relative stability and is also why benzene reacts with electrophiles. Acids are H+ ion donors. When they lose H+ ions, they form negatively charged ions, the conjugate base of the acid. Weak acids form an equilibrium between molecules of the acid and H+ ions and conjugate base ions in solutions. The stronger the weak acid, the more the position of equilibrium lies in the forward direction. Electrophiles are electron pair acceptors. They're usually positively charged and are attracted to areas of high electron density. Hydrogen bonds are intermolecular forces that can arise between hydrogen atoms in an OH, NH, or FH bond with an oxygen, nitrogen, or fluorine atom from another OH, NH, or FH bond. Recap done, let's go. Phenol is an aromatic compound, so contains a ring of delocalized electrons. It is essentially a benzene ring with an OH group attached. At first glance, phenol appears to be an alcohol, but this isn't the case. In organic chemistry, an alcohol is an aliphatic hydroxy compound. This is just a complicated way of saying an OH group is bonded to a hydrocarbon chain that has no delocalized electron ring in its structure, just like ethanol. The ring of delocalized electrons on phenol means it is classified as an aromatic hydroxy compound, and this ring changes everything. The ring of delocalized electrons in the benzene ring in phenol means the phenol is more vulnerable to electrophilic attack and will react with electrophiles. If a nucleophile came near the phenol, it would be repelled by the high electron density in the ring. One of the most interesting features of phenol, though, is its ability to act as a weak acid. This is a significant difference from alcohols and is a common area of exam questioning if your course includes phenol. When phenol behaves as a weak acid, it loses a H+ ion and becomes a phenolate ion. To understand why phenol is able to do this, it is easier to first look at why an alcohol such as ethanol is unable to. Let's imagine, hypothetically, ethanol could act as a weak acid and lose a H+ ion. If it did so, it would form a negative ion called an ethoxide ion, and there would be an equilibrium between ethanol, H+ ions, and ethoxide ions. The oxygen from the OH group would take the bonded pair of electrons from the OH bond for itself and become O-, with a full negative charge. The new lone pair of electrons don't have anywhere to go other than stay on the oxygen. And the carbon chain the oxygen is bonded to will give a positive inductive effect, basically pushing even more electron density to the oxygen. Now we have an oxygen atom absolutely loaded with electron density and a very localized negative charge. It will act as a strong base, stronger actually than a hydroxide ion. This all adds up to effectively render the ethanol such a weak acid that in reality it will never lose H+ ions and form ethoxide ions in solution. The position of equilibrium for the reaction would lie very far to the left, rendering the forward reaction basically non-existent. So why is phenol able to lose a H+ ion and form a phenolate ion if an alcohol like ethanol is unable to? The answer lies in that delocalized electron system in the benzene ring. When the OH group loses a H+ ion and a phenolate ion forms, the pair of electrons from the OH bond go to the oxygen. There would be an equilibrium established between phenol, H+ ions, and phenolate ions. However, now the extra lone pair of electrons on the oxygen spread a little into the delocalized system in the benzene ring. the benzene ring pulls electron density away from the oxygen. This reduces the ability of the phenolate ion to attract and rebond to H+ ions, meaning the position of equilibrium isn't so far to the left as for ethanol, and some phenolate ions are present at equilibrium. This is why phenol can act as a weak acid. The negative charge of the phenolate ion is spread out into the delocalized electron system, effectively stabilizing the ion and making it more likely to form. The other characteristic feature of phenol is its higher reactivity of electrophiles compared to benzene. As mentioned previously, a p orbital lone pair of electrons around the oxygen atom in phenol can be partially spread or be donated into the delocalized electron system. This increases the electron density in the benzene ring, making it more appealing to electrophiles. We say the benzene ring has been activated, and the OH group is considered to be an activating group. This reactivity of phenol with electrophiles compared to benzene is shown with specific reactions in different videos. See the links in the description below. Aside from the chemical properties of phenol already covered, there are a couple of physical properties that are relevant for chemistry at this level. Most notably, its low solubility in water. The hydroxy OH group in phenol enables it to form hydrogen bonds with water. However, the benzene ring is nonpolar and is unable to mix with water. There are basically two competing regions. One, the OH group, wants to mix and bond with water. The other, the nonpolar benzene ring, doesn't want to mix and is unable to bond with the water. Due to its larger size, relatively speaking, the benzene ring wins, and as a result, phenol has a low solubility in water. The hydrogen bonding that can arise between phenol molecules does give it a slightly higher melting point than would be expected for similar sized aromatic compounds. And as a result, it is a white solid at room temperature, with a melting point of 43 degrees Celsius. As an extra detail, when phenol mixes with aqueous iron chloride, a violet-coloured solution is formed. So, to summarise, phenol is a cyclic compound with the formula C6H5OH. It is essentially a benzene ring with an OH group attached. Phenol is able to act as a weak acid, as when it loses a H+ ion, the negative charge on the oxygen atom can be spread a little into the delocalized electron system of the benzene ring, making the phenolate ion more stable and likely to form. The OH group in phenol activates the benzene ring and makes it more likely to react with electrophiles than benzene. This happens as the lone pair of electrons on the oxygen atom spread slightly into the delocalized system in the benzene ring, increasing the electron density. Phenol has a low solubility in water due to the nonpolar benzene ring overriding the polar OH group that is able to form hydrogen bonds with the water molecules. Phenol is a white solid with a melting point of 43 degrees Celsius and forms a violet-coloured solution when mixed with aqueous iron trichloride. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.